Assalamualaikum warahmatullahi wabarakatuh. This is my final year project 1 video presentation. My name is Muhammad Muzaffar bin Aziz. I am from 4BKG section 1. My final year project title is Parameter Identification of a Coupled Tank Liquid Level System CTS. My supervisor is Madam Arfah Shahida binti Muhammad Noor. This slide will be divided into 5 sections, which is Introduction, Literature Review, Methodology, Early Result, and Conclusion. The introduction will explain the project background, problem statement, objective, and the scope of the project. Project background. The application of coupled tank liquid level system is tremendously, especially in chemical process industries such as petrochemical, paper making, pharmaceutical, and water treatment. The main objective of this system is to keep the liquid level at the process tank at a desired level. On the left is the oil refinery or petrochemical plant. On the right is the illustration of how the coupled tank liquid level system works in the industry. Problem statement. Level control is one of the most basic control strategies in most process plants. It is part of the inventory control to prevent accumulation in the systems or tanks. Think about it this way. We often need pump to drive liquid from one system to another. A pump will experience cavitation if the liquid level inside the tank falls below the threshold value, which in turn will damage the pump and of course could cause a big problem to the entire plant operation. Another example, the liquid level in tank has a very strong influence on the tank performance, and thus by controlling the liquid level, you can ensure that the tank involved can run on its optimum condition. In short, we often need to control liquid level in tanks not because for one to keep those levels constant, but such a control is a mandatory strategy to ensure that the entire system can run safely, smoothly, and profitably. First objective of this project is to develop mathematical modeling of coupled tank system by using system identification. Second is to analyze the stability and the transient response of the coupled tank liquid level system via closed loop and by using PID controller. The third objective is to design the PID controller for the coupled tank liquid level system. Scope. The scope of this project is to obtain the mathematical equation for a coupled tank liquid level system with single input, single output or seesaw configuration by using system identification. Next is to obtain the output response from the modeling function by using MATLAB software. Literature review. This section reviewed the journal and literature paper related to the project. First paper that I have reviewed is by Edilberto H. Vasquez and Martin A. Captcha 2016. The title is Closed Loop Identification in a 4-couple tank. Work done in this paper is to introduce a new method to achieve identification of a process in closed loop operation. Next is by Dian Murshida, Ahmad Faisal, Iwi Ismareda 2018. The title is Level Control in Coupled Tank System using PID Fuzzy Controller. The author did a research on fluid level control in coupled tank system using PID controller supported with fuzzy logic as tuner parameter of Kp, Ki, and Kd. Next is by Muhammad Fuad Rahmat, Sahazati Mat Ghazali 2008. The title is Modeling and Controller Design for a Coupled Tank Liquid Level System, Analysis and Comparison. Work done in this paper is to determine the mathematical model of a coupled tank system using system identification technique. The last paper that I have reviewed is by Nur Asmiza Slamat, Fiona Serena Daud, Haziq Izwan Jaafar, and Nur Hazah Shah Shamsuddin, 2018, where the title is Comparison of LQR and PID controller tuning using PSO for coupled tank system. The author did a research on system performance between PID and LQR control schemes for a coupled tank liquid level system with a particle swarm optimization (PSO) as the method of tuning. In methodology, we'll be discussing the project flow and the process carried out to obtain the preliminary results. There are 4 steps in my methodology, which is identify, setup, analysis, and design. In identify, first step is to obtain the mathematical modeling. Figure below shows a configuration that I use, which is a seesaw configuration. Next, the block diagram of the system is obtained, and from there we get the mathematical equation based on the block diagram. We set up the CTS002 with seesaw configuration where the input will be on tank 1 and the output will be on tank 2. The buffer between tank 1 and tank 2 is fully open. This is the back view of the coupled tank system. It shows the connection of the CTS002 to the microbox. Next, we calibrate the level sensor in both tanks by setting the pump voltage. The input to the pump motor is the voltage acting as the actuated signal that controls the input flow rate to each tank. The liquid then goes into the tank and causes the level to rise to a certain height. The level in the tank is measured using a sensor. We repeat the step for tank 2. After that, we did a calibration for the control inflow for both tanks. In MATLAB, we apply step input to the CTS by using sensory analog output to the microbox and obtain the output from the CTS. Unfortunately, due to current situation of pandemic, I have been to the lab once and the data that I have obtained is not satisfying. So I decided to take the output from one of my literature reviews as my reference or expected data. From there, we did a closed loop system by using transfer function from the reference paper. Water level is set to 15 cm. As you can see, the transient response is bad. Next, we designed the PID controller to obtain more robust transient response. There are 3 designs that I did. First is PID controller from the same reference paper that I referred for my transfer function. The transient response is better than before. Second is PID controller by using trial and error method. First, we set integral and derivative terms to 0 and increase the proportional gain until the output oscillates at a constant rate. Once the P response is fast enough, set the integral term so that the oscillation will be gradually reduced. Once P and I parameter have been set to desired value with minimal steady state error, increase the derivative gain until the system reacts quickly to its set point. The third design is PID controller by using automatic tuning method. Double click on the PID block and block parameter window will pop out. Next, click tune button and wait for several seconds for the linearization process. Click apply and we get the transient response of the system. As you can see, automatic tuning will produce an underdamped response, which indicates the transient response is not good. Early result. Transition response for the PID controller from reference paper. As you can see, the rush time is 2.369 seconds and the settling time is 6.379 seconds. Percent overshoot is 0% because of the critically damped response, and there is no steady state error. Next is the PID controller from trial and error tuning method. As you can see, the rise time is slightly slower, which is 2.489 seconds, and the settling time is 8.153 seconds. The percent overshoot and the steady state remain the same, which is 0% and 0 steady state error. The transition response for the PID controller from automatic tuning method shows that the rise time is 2.7 seconds, while the settling time is 49.9 seconds. Percent overshoot is 12.8% and steady state error is 0. Conclusion. This section concludes the result obtained. As you can see from section 4, PID controller that we obtained from reference paper is the best because it produces a better transition response. But the result obtained is not the final result. For future plan, I will be focusing on getting the mathematical expression from the couple tank system, and we need to put a new consideration into the design of PID controllers by considering robustness as a design specification. This is some of my bibliographical references, and that's all. Thank you.